Hello, and welcome to this presentation, Getting Started with the CMA180 ILS Testing. In this presentation, we'll cover how to configure ILS localizer and Glideslope signal generation on a Rohde Schwarz CMA180 radio test set. This presentation assumes a general technical familiarity with ILS localizer and Glideslope signals. If you're not already familiar with these signals, or if you'd like a brief review, you might want to watch the presentation Understanding ILS before beginning this presentation. The CMA180 option enables generation of avionics nav-aid signals, including the signals used in ILS or the Instrument Landing System. Both localizer and Glideslope signals can be generated, but note that only one of these can be active at a time. All ILS parameters are user configurable, and these include the RF frequency and level, the difference of depth of modulation, the sum of depth of modulation, the localizer COM ID signal, and many others. In the remainder of this presentation, we'll walk through how to configure these settings on the CMA180. ILS generation is started by going to the global toolbar and then selecting Avionics under the Analog tab. ILS configuration parameters are then accessed via the ILS tab. Once the main ILS configuration screen opens, the choice between localizer and Glideslope can be made using the tabs along the bottom of the screen. This is the main ILS configuration screen. At the top are the RFN connector configuration. Below these are the settings for configuring the localizer or Glideslope signals. Note again the tabs at the bottom of the screen for selecting either localizer or Glideslope. The Start-Stop button at the upper right is used to enable and disable signal generation. An info window below this graphically shows deviation from the center line or the Glideslope, similar to a cockpit instrument display. And on the bottom right, the optional ID signal can be enabled and configured. Let's now go through each of these areas step by step, starting with the RF and connector settings. The frequency of the ILS signal and the RF output level are entered under RF settings, and an external attenuation value can also be added to adjust for any gain or loss in the RF output path. If frequency pairment is checked, the frequencies in the localizer and Glideslope tabs will be paired or matched. Changing one will cause the other frequency to also be changed, as per the standard ICAO channel plan. In the center, under Connector Out, we can select which connectors are used for outputting the RF and/or AF ILS signal. Note that these can be enabled or disabled individually using checkboxes. The level setting in units of volts is the level of the audio frequency signal. And on the right, the checkbox Start Generator Automatically will cause the CMA to begin transmitting the ILS signal as soon as the Generator tab is selected. By default, the CMA180 generates both the 90 Hz and the 150 Hz lobes of the localizer signal. It is, however, possible to uncheck either of these boxes and have the CMA generate only one of the lobes. The frequency of each lobe can be changed individually, and the phase offset defines the phase difference between the signals in each lobe. None of these parameters need to be modified when generating standard localizer signals. The parameters DDM, or difference in depth of modulation, and SDM, or sum of depth of modulation, are however important when generating localizer signals, and therefore we'll spend the next few slides explaining or reviewing these in a bit more detail. Recall that both lobes of a localizer signal are AM modulated, the left lobe at 90 Hz and the right lobe at 150 Hz. The modulation depth of each lobe is different depending on our position within the lobe. On the runway center line, both lobes have the same AM modulation depth of 20%. As we move to the right of the center line, the AM modulation depth of the 150 Hz lobe increases, and the AM modulation depth of the 90 Hz lobe decreases. For example, at this point, the modulation depth of the 150 Hz lobe has increased to 30%, and the depth of the 90 Hz lobe has decreased to 10%. And at the far right edge of the localizer pattern, we see the 150 Hz lobe at 40% AM modulation depth, with zero modulation depth, so to speak, on the 90 Hz lobe. The localizer determines position deviation from the center line using the difference in depth of modulation between these two lobes. Mathematically, we can say that difference in depth of modulation is the measured 90 Hz AM modulation depth minus the measured 150 Hz AM modulation depth divided by 100. Related to DDM is something called SDM, or sum of depth of modulation, which is a sum of the modulation depth of each lobe, again divided by 100. So an aircraft that is exactly centered on the runway centerline will see the same AM modulation depth on both lobes, and the difference in depth of modulation, or DDM, will be 0. Moving to the left of the center line, that is more into the 90 Hz lobe, causes DDM to increase or become more positive. Moving to the right of the center line, or more into the 150 Hz lobe, causes DDM to decrease or become more negative. These changes in DDM are what cause the needle to move right and left on a localizer display. Difference in depth of modulation can be expressed in three different ways: DDM depth, DDM percent, and DDM current. DDM current refers to the amount of current supplied to the localizer gauge, or dial. The amount of left-right needle deflection is a function of this current. The conversion between units is done using simple formulas. Note that the 967.75 microampere conversion value is derived from the standard 150 microamps value at a DDM of 15.5%, which is the difference in depth of modulation normally seen at the outer edge of an ILS course sector. DDM is closely related to something called fly mode. Fly mode is simply an indication of which direction the pilot needs to fly in order to intercept the localizer centerline. This is based on the current value of DDM. If fly mode shows right, this means that the 90 Hz lobe is dominant, DDM is positive, and therefore the pilot must fly right to intercept the center line. If fly mode shows left, then the 150 Hz lobe is dominant, DDM is negative, and the pilot has to fly left to center the aircraft with the runway centerline. Note that the fly mode on the CMA180 is an indication rather than a configuration parameter. Now that we've covered localizer, let's move on to discussing glide slope. As previously noted, most of the concepts in localizer apply to glide slope signals as well. The basic glide slope signal settings work the same way for glide slope as they do for localizer. They allow changing the frequency of the two lobes, turning one of the lobes off, and changing the phase between the lobes. Again, these are analogous to the basic settings for localizer. Glide slope is also analogous to localizer when it comes to difference in depth of modulation, but with one important difference. The standard AM modulation depth along the glide slope is 40% for each lobe, as opposed to the 20% standard modulation depth seen on the localizer centerline. The formula for DDM is, however, the same in both cases. As with localizer, an aircraft on the glide slope will see the same depth of modulation from both lobes, and DDM will be 0. Flying above the glide slope moves the plane more into the 90 Hz lobe, and DDM increases. Flying below the glide slope moves the plane more into the 150 Hz lobe, causing a decrease in DDM. Similar to the way the localizer works, the glide slope needle is controlled by these changes in DDM. The fly mode in glide slope works much the same way as it does for localizer. If the difference in depth of modulation is positive, this means the aircraft is above the glide slope and the pilot should fly down. Conversely, if DDM is negative, this means the aircraft is below the glide slope and the pilot should fly up. Most of the other glide slope amplitude settings on the CMA have the same meaning or effect as their localizer counterparts. There are, however, two differences to make note of. First, the default sum of depth of modulation for glide slope is 80%. This is different from the value of 40% in Localizer. The second is that the DDM glide slope current is calculated using the scaling factor 857.125 microamperes. In Localizer, the scaling factor was 967.75 microamperes. One last feature of the ILS signal generator functionality is the info pane. This is a graphical depiction of localizer or glide slope needles as a function of DDM. For localizer, this info pane shows DDM graphically using a localizer style display and a fly right left indication. For glide slope, DDM and fly up down is shown using a vertical glide slope style display. The final configuration parameter we'll look at is the COM-ID signal, which is used by pilots to ensure that they are tuned to the proper ILS localizer. Localizers transmit this ID signal as Morse code, but for testing purposes, a simple AM modulated tone is often used as the ID signal. On the CMA180, the frequency of this tone and the modulation depth can be configured. Enabling the ID signal will cause this tone to be heard when the ILS receiver is tuned to the signal frequency. Let's end with a brief summary. The Rohde Schwarz CM180 radio test set can be used to generate standard and customized ILS localizer and glide slope signals. This requires software option K180. Note too that only one component, that is either localizer or a glide slope, can be active at a time. The most important parameter in both cases is the difference in depth of modulation, or DDM, which provides left-right or up-down guidance. The CMA180 does, however, offer complete control over all parameters for each lobe in localizer and glide slope signals. And finally, a localizer COM-ID signal can also be configured. This concludes our presentation, getting started with the CMA180 ILS testing. If you'd like to learn more about ILS, other navigational aids, or the CMA180 radio test set, please see the links in the video description.
Thanks for watching. Please subscribe to our YouTube channel and visit us at rohde-schwarz.com.